Hey everybody, welcome back to Organic Chemistry. Now this is the last section for Chapter 6. This is the summary of Sn1, Sn2. And we're also going to learn about what's known as intramolecular versus inter and competition reactions. And then we'll wrap up with a few last problems. So let's get started. So the first thing we're going to do is just a quick summary. And here's our summary card that we're going to work from. Okay, now what I want to emphasize here is that we don't know E1 and E2 until Chapter 7. We're going to learn about that. But for now, we know these two here. Okay? And as you can see, there are certain things to identify. First off, when it comes to the alkyl group, notice that this Sn1 is the complete opposite of Sn2. Tertiary, secondary. Tertiary is best, whereas here, methyl's best, and secondary is the worst. So these are the opposite. It's very clear if it's tertiary, it could never be Sn2. Just like if it's primary, it could never be Sn1. So that's very easy. The trick is when it's secondary. That's when we're going to have the most difficulty, and I'll show you how we figure that out. Okay? But tertiary, it's easy. Primary and methyl, it's easy because it could never be Sn1. And that's that. Leaving group is the same for all of them, right? So no matter what reaction here, it's always going to be the same trend. Okay. The nucleophile is what makes the difference between these two, for sure. That's always the first place I look. If the nucleophile is strong, and we have a list of 6 things that tell us when it's strong, I'm not going to go through all 6 of them now. We've seen that already in our review sheet. But remember, there's 6 things to consider. Whereas if it's weak, meaning it's neutral, then it's an Sn1. But if it's negative or any of those trends that we discuss, usually negative is the most common, then it's Sn2. Solvent, although here, it's really not as important. Sometimes the solvents are misleading. They give you a protic solvent in a Sn2 reaction, but it really doesn't matter. This is what's preferred, and if this is the only difference, then you go with the solvent. But if there's something different here, then you would ignore this. So the trend that you want to work is top down. This is the first priority. Then you look here. Then you look here. And then you get to solvent. You see that? So solvent is the least important priority for us. Stereochemistry between these two, you could see that this Sn1 always gives you a racemic mixture of different isomers, whereas this one only gives one answer. It'll be the opposite of the stereochem you began with. Okay, so this is the comparison between these two, and when we do problems, we'll learn how to figure out whether it's Sn1 or Sn2. Now, the next thing I want to talk about is what's known as intramolecular versus inter. Now, for example, let's say I have an alkyl bromide, and notice how this is secondary, right? So I would not know right now if this is Sn1 or Sn2, but let's say I put over this a CH3O-. Okay? Now, looking at our card, we can see the difference. So the secondary could be any one of them, right? Sn1 or Sn2. But since it's negative, it's a strong nucleophile. Negative is strong. So that tells me that this must be Sn2. See that? This must, no matter what I put, even if I put methanol down here, when you look at this, you're going to say, okay, this is my nucleophile right there. And it's negative, right? So negative will dominate over the other characteristics. So negative versus neutral, negative wins. This must be Sn2. Okay, it must be Sn2 because it's got that strong nucleophile. If I only had that, then it must be Sn1 because now there's no negative. It's a neutral nucleophile and a solvent. Okay. But notice that even though this is a protic solvent, it's still Sn2. Okay, even though it's a protic solvent. Like I said, the solvent is where they tend to trick people because it's the least important rule. And so although it likes a protic, you can see protic solvents as well, right? Protic is OH or NH solvents, like water, alcohol, ammonia, so on. Okay, now, this right here is known as an intermolecular reaction. Now, what do I mean by that? Inter tells me that we're going to take 2 things that have absolutely nothing to do with each other, 2 different reactants, and bring them together. So when this reacts, notice how this is going to come in and the Br is going to leave. Now let's say this is on a wedge so we can do stereochem. Well then, when this methoxide CH3O- comes in, it comes in from the back, and only the back, right? So that plus Br- is our answer. Now, notice that this piece here and this piece here, the substrate and the nucleophile, they have nothing to do with each other. They're not connected. They're two separate molecules. That's known as an intermolecular. Now, what if instead I have an example like this, which is going to be known as an intramolecular. Intra means within itself. So intramolecular reaction. Now, how would I do that? Well, imagine if I had a system like that, and let's say there's a Br here, and there's an OCH3 or an OH here. And now this is going to react, actually even better, let's make this negative. So this is negative. And it's going to react with some sort of solution, let's say alcohol, because it doesn't matter. This is what's known as an intramolecular, because when you look at this, we have a leaving group and we have a nucleophile, a strong one, right? This is a nucleophile, this is a leaving group on the same molecule. Now you might say, well, what about this one here? Well, that's a solution, and because negative is better than neutral, we're not even going to think about the alcohol, right? If they were both neutral, if this was an OH, then maybe the alcohol would win, but actually it turns out it still wouldn't win, but I'm going to go over that next. Let's first start here. So the fact is that this has a nucleophile and a leaving group on the same, within the same molecule. So what that means, so let me kind of put some branch over here so you could see. What this means is that we're going to have the oxygen come in and attack the carbon with Br. Now, notice that this is primary, so this has to be Sn2. It can't be Sn1 because primary would never happen with Sn1, right? So what's going to happen here is this O is going to come after the carbon that's primary while the Br leaves. Now, that's going to make a ring. Intramolecular reactions make rings, always. Think about like as if your finger, extend your arm straight out, and the tip, your pointer finger, have it touch your shoulder. Notice that when you do that, you extend you make like a circle with your arm, like making an arm muscle. And so what we're doing is, like, for example, if you have like right here your finger, see how like this is my strong arm muscle here, so this is my face right here, right? So if I want to touch my shoulder, I'm making a circle. This right here is a ring right there. I know this is not the best drawing in the world, but you know, you get the point. Let me give myself some chest muscles and some six-pack and so on. All right, that's it. I think it's enough, right? There you go. I don't know. It looks like art, but I don't know what it is. Anyway, so this is an intramolecular reaction, right? Because I have the oxygen folding in and the Br leaving. So how do I track this? Well, the best way to do it is to number 1 for the atom, that's the nucleophile, and then work your way over to the carbon that has the leaving group. So now I know I'm about to make a 5-membered ring. That's the distance between oxygen 1 and then either 2, 3, 4, 5, or even counterclockwise or clockwise, doesn't matter. But that's my connections. So 5 had a halogen, but it's gone. 1 is the oxygen. And now 4, let's put back in its branch. See how I did that? As long as I count from left to right or right to left, I number this out, I can make a nice clean 5-membered ring and make it connect in. So this is known as an intramolecular. Look at the difference. Here, this has nothing to do with the carbon system, the substrate. Whereas here, the substrate has both pieces, the nucleophile and the leaving group. Okay, so that's what's known as an intramolecular reaction. All right, and again, let me just show you another rule. So, what if we can have an intra or inter reaction? Okay, so how do you know what to do? So let's say we have this right here, and let's put a Br right there, and